My name is Gosia Konwerska. I work for Wolfram Research with the probability and statistics team. And I would like to talk a bit now about time series. So the abstract is very straightforward. And, it tells me only that I need to magnify. So this is not the first talk. And the time series function, about time series and temporal data in Wolfram language. And this is not a new object in Wolfram language. And so I'm taking some liberty to actually show you some examples and case studies, maybe about examples on different ways to use these objects, and also how to use different processing functions about that. So is there some problem? No. It's good? Please come forward. The only thing I can do is to make the whole thing 150. Then it's not going to fit on the screen. So that's a table to summarize kind of what we have. So color tells you we have time series, event series, temporal data, although the head for all these objects is temporal data. I know it's a kind of confusing thing, but there is a way to work around it and kind of keep track of what is what. So there are differences between each of these objects, and there are like few main things that I put here. Time series and event series are a single path objects only, while temporal data allows you to store multiple paths. When we query an object at the given timestamp, the time series and event series will return a value, while temporal data will return data distribution. I will show an example for that too. Then the question is, what happens when you query an object in between the existing timestamps? And the time series will interpolate, the event series will not interpolate, will return missing, and temporal data will also interpolate in a way that its order will be 0, so it just returns the previous value, also known as hold from the left. So first I'm going to talk about time series, usually used to store some physical quantities, and I have an example here about the length of the daylight. We have fall. The days are shorter. It makes me depressed, so I think about these things. We can have a property of the sun, the daily time above the horizon. And today this is 10 hours, 58 minutes. Yesterday it was 11 hours, so the days are getting shorter. Indeed, and you can see that I can have sun dated. So I can have these properties, at any kind of given time. And because this is an astronomical computable property, I can have it in the future, I can have it in the past, because that's computed. And so what I did here, I computed the time series for the whole 2018. And this commented code this is how I did it, but I don't want to kind of reproduce that. So I just had the time series. And also this notebook will be available on the Puffable, so you can always reevaluate this for yourself. And so we have the time series. The property first value gives me exactly what it says first value, so that's 9 hours, 18 minutes, so more or less the 1st of January, length of the day. First date though, when you look carefully, it is 1st of January, but what it tells you, which year? It tells you 1900s. And when you look at the creation of the time series, is that I didn't really provide dates to be specified, the timestamps to be specified for this time series. And when you look whether they actually have dates, they don't. So what happened here is that all this information about the length of the day is stored in terms of integers. So just enumerated the observations. But this is not completely lost case, because we can rescale the time series to put dates in on the timestamps. So take the time series rescale, apply to the existing time series, and just give the starting date, the ending date, and then the step in which we would like to rescale our time series. And then we have dates where our first date is really January 2018, as you can see. And And so we have fixed the timestamps. The other thing is that, as you noticed, the daylight was given in a mixed units, hours and minutes. Maybe this is not the best. We can also apply unit convert over the whole time series to change to hours. Then the first value is just some fraction value in terms of hours. We can compute the mean, and then we can plot this time series using the date at least plot to see how the daylight is, the length of the day is changing. Right. Okay. Another case that is also popular, it's the financial data. So the thing is that when we do the day trading, the price of the stock is not changing from day to day really. So especially when you have a closing price or an opening price, nothing is changing. So it would make more sense to actually use temporal data. But because we are also interested in accessing the values on a given timestamp, it may be more maybe better to actually use time series, but change the interpolation, like the resampling. So we don't really have the linear interpolation, which is the default for the time series. So this is some stock, probably some computer company being traded, and you kind of see the plot. And what I have here, it's the date path, and this is the first 5 observations. And so what we can see that this is Wednesday, Wednesday, Thursday, Friday, and the next one is Monday, right? So the point is that the resampling time by default, as the time series were created, is just linear interpolation. So if I ask what is the value on Saturday, so January 5th, I'm going to get a value which is interpolated between Friday and Monday, right? And we know that nothing changed. So the way to go around it is to define new time series, taking into argument our existing time series and just resetting the resampling method to hold from the left. And then when you take this closing and query this on Saturday, we're gonna get the same value as there was on Friday, the 34.38. So that solves the interpolation, and yet we always get the value on a given date. Another issue that we kind of see with this time series, these objects, is that the trading happens on business days, not on the days. That's what we just saw. There was no information for Saturday and Sunday, and so when you look now at this new time series that just holds from the left, still this is not a regularly sampled object. That means that there are different. The differences between timestamps are not the same. And when you look at the minimum time increment, it gives you 1 day, because yes, between Monday and Tuesday, it's 1 day. But we really should think about business days for this type of data. And there are 2 ways to kind of fix this time series. One of that is to redefine time series. So I take the time series, take the values, define then, this is important bit here, define the new range for the timestamps when our step is by business day, okay? And another important bit here is to specify holiday calendar, okay? So we know these business days are according to, the proper stock exchange, if these are the stocks, and such. So we, in Wolfram language, we have some of the trading holiday calendars, and I would like to point out that this is not equivalent to the federal United States holiday calendar. The holidays are different. So that's one way. And another way is to basically use the time series resample that looks, I think, easier on the eyes by business days. And also important bit, specify the New York Stock Exchange holiday calendar. And then when you see the increment, the minimum increment is now business day. They are regularly sampled in both cases, and what is important, the path didn't change. So when you look at just the dates and the values on these dates, this is exactly the same as we started. And yet we know that this series is regularly sampled, and we also know that it keeps the value from the left. And when we have the regularly sampled time series, then we can actually trust the estimation, the modeling, And so this is applying the time series model fit to one of this resampled time series. When you do this with the original data that was not regularly sampled, you're going to get this nice information that we are resampling this for you. But you really have no control how. And in a way, but you see the information that's resampled at the resolution of the minimum time increment, and you know it was a day, not a business day. So that may be not what you want for your data. These are the models. You can see that the model 2, because it was resampled on the day, will have, put in Saturday and Sundays on so. What is interesting is to kind of have a forecast the trends, and when you model the resampled data, it actually models the forecast in business days. When you forecast the non-sample data that was resampled into every single day, it's going to give you a forecast in terms of steps that are days. So that's something to keep in mind. Okay, event series. This is a bit lighter stuff, and because what we can do, we can have really as a values almost anything well, actually even in time series, but especially for the event series. So this is event series of the birthdays of American presidents. And to actually get this example right, I had to learn some trivia. We currently have the 45th president, but there were only 44 presidents because Grover Cleveland was a president twice, but not in a consecutive terms. And when he became a president again, that he had a new number. That's why our numbering system is not in agreement with the number of human beings that served at this office. So what we can do to study this event series, one thing is to use timeline plot. You can see the dates, so where the presidents were born. We can also use this timeline plot with association thread to have the values and dates, and then it gives you this nice thing here telling you when was born. What I find interesting from the statistical point of view is the birthday distribution within the year. And date histogram with the date reduction is really cool for that. And it works just directly on the event series. And you see that people born in September have really low chances. And I was born in September and it was crashing. I was also not born in this country, but that's a different story. And another fun factoids that we can do, especially with the event series, is to work with dates again. But I was looking at the dates when Thanksgivings happen. And we know that Thanksgiving now is on Thursday, but that was not always the case. And also having some data knowledge encoded in a Wolfram language, you can actually access some interesting information. So the first year it happened was 1619. Again, my commented out code is a query to Wolfram Alpha to actually extract all the dates for the Thanksgivings, and then I just get the event series. And the thing is that the timestamps are actually the exact dates when Thanksgiving happened, but the values is the number, which is the year. And when you plot this on a timeline plot, it kind of looks continuous because this is a lot of points. So again, what can we do to kind of analyze this data better, these dates? So again, date histogram with date reduction in a week tells us, yes, Thursday is the dominating day of the week, but Thanksgiving without the pi, it's not complete. So what I did here is to use a time series map thread, which allows us to apply a function on the timestamps. And so to take the date value, which is of the timestamp, which is the day name. And so I have a new event series, which basically will just have values, which are the names of the weekdays, Tuesday, Monday. And when we tally the values, we can see how many times on each given day the Thanksgiving happened. And that's my favorite thing, the pi. So you can see that, yes, Thursday dominates. And the other thing, what we can do is to gather now the weekday, like this is the weekday event series based on exactly the weekday, and then sort that by the weekday. And in that way, I create kind of 7 7 feeds in that way, or I can say, and plot, again on the timeline plot, that each data feed is for a given day of the week. And so I think that the first day established itself at the end of or during the Civil War. Another interesting trivia. And then, so how many days between Thanksgivings? Another application of the moving map, and can plot a histogram, and then 30 more days this year till Thanksgiving. So, okay, temporal data. As I mentioned at the beginning, temporal data on a given timestamp query returns data distribution, because the original design for the temporal data was to store simulations of the random processes. And so random process in question were really a time series processes, just like here this is ARMA process. And when you evaluate random functions, so get a simulation, it gives us a single path, and this is stored as a temporal data. And in simulation world, we sometimes want to simulate more than just one path, so we have more observations, so either 5. And if you have more paths, like here, we have 1,000 paths, right? We can do some statistics for, like slicing the path at a given timestamp. So the slice distribution will be exactly accessing the temporal data at time 10. So this is exactly what happens when you query at the given timestamp. We get the data distribution. We can compute the mean of this distribution, and we can plot, for example, CDF. We can also get slice data. That's the property, the slice data, and it's going to be a list. And this list will have 1,000 elements because we had 1,000 paths. So kind of slice in that way. And what we can do, we can plot a histogram for this slice data, and we can study the distribution for a given time.
What happens if you don't have the same time on the files?
Okay, so if you don't have the same timestamps, you can still put it together in one object of temporal data. This is okay because they don't, the number of how to say, the number of paths. So I need to have enough, like the same amount of values and the same amount of timestamps, so they are matching.
In the previous example, you took the main at point 10.
Yes.
Time equal 10, but not all passes must have a value.
Exactly. So what I'm saying, that if you have this multiple paths that they don't have the matching timestamps, and if you query something at the given time, what happens is that you're gonna get either interpolated value. And if this is temporal data, and only temporal data allows multiple paths, you're gonna have the value hold from the left. So it's gonna fill the blanks if you don't have the exact timestamps. It's just gonna give you the previous value.
It happens automatically.
It's automatically, but you as a user of temporal data can change that behavior. So that is controlled by the resampling method, and you can put different order. It can be linear. Temporal data can interpolate linearly, quadratically. It can return missing. That's full flexibility there. Yes. Mm-hmm. So, okay. No, this is maybe a bit more technical issue, but I think it's important. It's about resampling, and I mentioned this a bit already in the previous examples. This is a time series of four values, A, B, C, D, and 4 times, which are given explicitly, 1, 3, 4, 4.5. And so you can see that this is not regularly sampled. And regularly sampled Q is a top-level function that can tell you, but also there is a property called uniformly spaced Q among the properties that can also give you this information about the uniform sampling. This list of properties is called developer properties, and it's called this for a reason, because most mortal human beings don't need all of them. And this list is kind of flexible as I add stuff as I need, and might actually promote some of those into the proper properties. But for people who are using and want to have finer control of the temporal data, I think this is useful to know that all of this is available. And so. One of the things that in this, from this list, the property that tells you a lot about the timestamps is the so-called unexpanded row times. And in this way, we'll see that because our timestamps are not regular, they couldn't be packed in any nice range. We have to keep all the lists, together. If I take this new time series here, which is just regular time series, the same values but starts at 0 and automatically will have the times 0, 1, 2, 3. And when you compare unexpanded row times with the times, you see that they're different. And the unexpanded row times are actually stored in the form of a range and a step. And this is also a quick comparison of the default resampling methods. So time series, event series, temporal data, exactly the same values, exactly the same timestamps. And then resampling with respect to the minimum time increment. And then basically see what happens. Linear interpolation for the time series, missing for the event series, or AA holding the value from the left for the temporal data. This has far-going consequences if you want to use accumulate differences on any filters coming from the signal processing, okay? Because all this, you see that what I have here is accumulate on the time series and get the values, or accumulate just the values and you're gonna see the differences. Because accumulate and differences assume that things are regularly kind of fed to them, so they require them to be in regular steps. And I think I'm a little bit more time. So this is to kind of let people know that this is gonna happen, and that's why being aware of what your resampling method is very important, and also whether you're gonna feed the whole time series temporal data into this function or only operate on values. Okay? And one more thing is about the missing data method. Because what happens in the real world is that we often get the data. In this case, this is weather data feed temperature. I get the time series already from the weather data. And now the question is, do I know if I have missing or not? Do I have all the values? So how to find out? Well, when we plot them, we kind of see the holes. There's some holes here on the plot. But like the really, really fast way to do it is to compute the mean. Because the mean will tell you that it has missing in it. And it's not going to be really meaningful. Okay? And there are ways to deal with that. And I'm going to show you a few. And we can create new time series object with the existing time series object, specifying missing data method. And in this way, I am filling all the missing with a constant pi. Okay? This is, again, not very meaningful. I'm not saying it makes sense for this data, but it's an example that makes sense for some other, in other cases. So it's 300 pi's. We know we had 300 missing. Okay? We can also specify automatic, okay? And then Wolfram language will do it for you. This is the way that the missing is filled is the same way as the resampling type specified. So if there is a missing, then the automatic missing data method will interpolate. And for the time series, it's going to be linear interpolation. So if I do it directly like that, specify missing data method as interpolation with order 1, I get exactly the same mean as the automatic method. We can use different interpolation method, interpolation order to be 2. The mean changes a bit. We can also use moving map in a way to replace all the missing with the mean of the non-missing values and get the meaningful mean, or delete all the missing from the time series, and then we got exactly the kind of the same mean because that was computed by the mean of the non-missing values. And I am done here, so thank you very much.